Hello everyone, this is Vibhushi Suprit from CSEF section. In this presentation, we will explore a parallel algorithm for the diagonalization of symmetric practices, highlighting its significance and benefits in the realm of parallel computing. Optimizing neural network training with parallel computing. Neural network training is a computational intensive process that can benefit from parallel computing. This presentation will explore techniques for optimizing neural network training with parallel computing and discuss the advantages and challenges of using this approach. To optimize neural network training with parallel computing, consider using frameworks like TensorFlow or PyTorch that support distributed training, utilize multiple GPUs or TPUs to parallelize the computation, speeding up training by dividing the workload. Implement data parallelism or model parallelism based on the architecture and resources available. Additionally, explore tools like Forward for distributed training and ensure efficient communication between nodes. Regularly monitor and adjust the parallelization strategy for optimal performances. Accelerating model inference with hardware accelerators. Model inference is a key step in the deployment of machine learning models. Hardware accelerators can speed up the inference process and reduce latency. This card explores the benefits and challenges of using hardware accelerators for model inference. Improving model accuracy with ensemble methods. Utilize frameworks like TensorFlow or PyTorch that support GPU acceleration. Transfer the model to the GPU for faster inference, particularly beneficial for deep learning models. If applicable, consider using tensor processing units designed by Google for machine learning workloads. CPUs can significantly speed up inference for models trained on Google Cloud, reduce precision for model weights and activations without compromising much on accuracy. This can make the model more suitable for hardware accelerators, improving inference speed. Remove unnecessary weights or neurons from the model. Smaller models require less computation, leading to faster inference on hardware accelerators. Enjoy compiler optimizations tailored for specific hardware platforms. This ensures that the model is efficiently translated into instructions that can be executed on the target hardware. Leverage libraries optimized for specific hardware such as CUDNN or for NVIDIA GPUs or OpenVINO for Intel processors. These libraries provide low-level optimizations for deep learning workloads. Deploy models on edge devices equipped with specialized hardware accelerators. This reduces latency by performing inference locally rather than relying on cloud-based services. If applicable, parallelize inference across multiple hardware accelerators. This can be achieved by splitting the input data across devices, regulating the results. Ensemble methods combine multiple machine learning models to improve accuracy and reduce bias. This card discusses the benefits and techniques of using ensemble methods in model development and deployment. Description of symmetric matrices. Symmetric matrices possess a special property where the elements mirror each other across the main diagonal. This property allows for efficient manipulation and analysis of data in various mathematical and computational applications. By combining a symmetric matrix is a square matrix that is equal to its transpose. In other words, a matrix A is symmetric if A transpose equals to A. This symmetry results in a pattern where the elements above and below the main diagonal are mirror images of each other. Mathematically, for a symmetric matrix, A equals to Aij of size n or order. In simple terms, the elements said that ith row and jth row are the rows and columns respectively. Importance of diagonalization. Diagonalization is a powerful technique that simplifies the analysis and computation of symmetric matrices. By transforming a matrix into a diagonal form, we can extract valuable information about its eigenvectors and eigenvalues, enabling efficient calculations and problem solving. Diagonalization allows expressing a square matrix as the product of where P is the matrix of eigenvectors of A and D is the diagonal matrix consisting of the corresponding eigenvalues. This decomposition simplifies matrix operations, making it easier to analyze and manipulate the matrix. Diagonalization can be used to solve systems of linear equations, transforming the system of equations using the diagonalization from simplifies calculations and can make solving the system more straightforward. Computing powers of a matrix becomes simpler when the matrix is diagonalizable. Is the diagonal matrix obtained by raising each element to the power dn. Diagonal matrices are particularly convenient for computations because they only involve scalar operations on the diagonal elements. This can significantly speed up certain mathematical operations and algorithms. Overview of parallel algorithms. Parallel algorithms utilize multiple processing units to perform computations simultaneously, significantly reducing the overall computation time. By leveraging parallelism, computation tasks can be divided and conquered more efficiently, leading to enhanced performance and scalability. A parallel algorithm is a computational algorithm that divides a problem into subproblems and solves them simultaneously. Often using multiple processors or processing units, the primary goal is to achieve improved performance by exploiting parallel processing capabilities. Here's an overview of key aspects of parallel algorithms. Decomposes the overall task into smaller independent tasks that can be executed concurrently. Involves distributing data across multiple processors and performing the same operation on different portions simultaneously. Processors share a common memory space and communicate through shared variables. Each processor has its own memory and communication is achieved through message passing. A problem breaks a problem into subproblems, solves them independently, and combines the result. Divides the computation into stages, and each stage can be processed concurrently. Assigns independent tasks to different processors for parallel execution. Parallel distributes loop iterations across processors to achieve parallelism. Ensuring that work is evenly distributed among processors to avoid idle time. Coordinating the execution of parallel tasks to maintain consistency. Managing data exchange between processors efficiently. Ensuring that the performance scales as more processors are added. Measures how much faster a parallel algorithm is compared to its equivalential counterpart. Examines the utilization of resource to achieve speed up. Benefits of parallel computing. Parallel computing offers several advantages, including increased speed, improved scalability, and the ability to handle large data sets and complex computations. It allows for efficient resource utilization, making it a valuable solution for high performance computing device. Description on parallel algorithms. Our parallel algorithm partitions the matrix into smaller submatrices, assign each submatrix separate processing unit for simultaneous computation. Through efficient communication and synchronization methods, the submatrices are then combined to obtain the final diagonal form. The algorithm includes steps such as matrix partitioning, parallel computation of eigenvalues and eigenvectors, and reassembly of the diagonalized matrix. These steps are carefully designed to maximize parallelism and minimize communication method. Our parallel algorithm exhibits favorable time complexity. significantly reducing the computation time compared to traditional sequential algorithms. Additionally, by leveraging parallelism, it effectively utilizes the available computational resources, optimizing space usage. Performance analysis comparison with sequential algorithm. We conducted extensive performance comparisons between our parallel algorithm and the traditional sequential algorithm. The results showcased a remarkable speed up and demonstrated the efficiency of our parallel approach in handling large symmetric matrices. Our parallel algorithm exhibits excellent scalability, allowing it to handle increasingly large matrices with minimal impact on performance. This summary of we have explored a parallel algorithm for diagonalization symmetric matrices, uncovering its advantages in terms of performance, scalability, and efficient resource utilization. This algorithm offers a powerful solution for computing complex problems involving symmetric matrices. While our parallel algorithm showcases remarkable results, further research can focus on optimizing it for specific hardware architectures and exploring parallelization technique for other matrix types. This continuous improvement will enhance the applicability and effectiveness of parallel computing in diverse domains. Parallel algorithms can scale with the addition of more processors or processing units. This scalability allows systems to handle large workloads and datasets efficiently. Multiple processors working concurrently enable higher output, allowing the system to handle more tasks in a given time frame. Parallel computing system efficiently share computational resources, maximize the utilization of processors and memory. Parallel computing is well suited for applications that involve processing large data sets. Each processor can work on a different portion of the data simultaneously, accelerating the analysis. Parallel algorithms, particularly those following the divide and conquer paradigm, simplify the solution of complex problems by breaking them into manageable subproblems. Thank you.